When you open a digital document today, you expect this sort of, well, a kind of mathematical perfection,
Right,
right?
absolutely.
Like you load a PDF on your screen and you just assume the margins are going to be completely parallel, the fonts will be razor sharp, and, every single line of text is perfectly aligned.
Right, we just take that total uniformity for granted now, like it just happens by magic.
Exactly. But making that happen, making that digital perfection a reality, it actually requires forcing organic, messy human communication into these incredibly rigid structures. And that's what we're getting into today. Welcome to the deep dive.
It is a great topic today.
Yeah, we are looking at a highly specific, honestly pretty granular developer log. It's an excerpt from a series called Notes-on-Haskell-Programming, specifically part 174, which was written by a developer named Ang and published on June 30th, 2026.
And I know what you're thinking at home. You hear Haskell Programming Part 174, and you might want to run for the hills.
Right, it sounds a bit intense.
It does, but our mission in this deep dive is actually incredibly relatable. We're going to explore how a really frustrating real-world formatting issue specifically, this messy alignment in a digital table of contents, forces a programmer to literally surgically dissect human language just to turn it into machine-readable data.
Yeah, and even if you have, never touched a single line of Haskell in your life, or any code for that matter, this source is just this fantastic window into the hidden architecture behind the documents you read every single day.
It really is. It shows the extreme lengths developers have to go to just to make human language play nicely with digital formats.
Okay, let's unpack this. We need to start with the actual visual problem first,
Yeah.
right? Because before we look at the code, we have to understand what triggered this entire architectural rethink for Ang.
Right, you have to see the headache from the developer's point of view.
Exactly. So Ang is currently working on an ebook generation process. They are generating PDFs, and they hit a massive roadblock with the table of contents.
And it's always the table of contents that gets you.
It really is. So the issue is that the Chinese chapter numbers in this book are causing completely inconsistent alignment down the page.
Yeah.
Like the right side of the text is just jagged.
Right, which looks terrible if you're aiming for a professional product.
Yeah, the stated goal here is a uniform professional look. So Ang decides, okay, to fix this, I need to convert these Chinese characters into standard numerical digits, like swapping out the character for 300 with the actual digits 300.
What's fascinating here is how a tiny visual inconsistency, right, just a slightly jagged margin, prompts this massive shift in how the developer has to handle the raw data.
It's like pulling a loose thread on a sweater.
Yes. It highlights this classic tension in technology between aesthetic design wanting a clean, perfect table of contents and unpredictable human information. You want a perfect grid, but your raw material is made up of text characters of wildly varying widths and meanings.
Think of it like, okay, imagine you're trying to perfectly align a gallery wall in your living room.
Okay, I'm picturing it.
You want this neat, Instagram-worthy grid of pictures, but instead of standard rectangular frames, someone hands you frames of wildly unpredictable shapes and sizes.
Oh, man, sounds like a nightmare.
Right. Some are tiny triangles, some are massive ovals, some are these jagged abstract shapes, and you are being told to force them into a rigid, perfect rectangular layout. It's just not going to work.
It's going to look like a mess.
Exactly. But I have to push back here, or play devil's advocate. Why does something as simple as a chapter number completely break a digital table of contents? I mean, a computer processes millions of calculations a second, right? Why does it stumble over a chapter number that a human reader understands instantly?
That is the core issue right there. It's because humans read for semantic meaning, while computers read for structure.
Okay, break that down for me.
So when you look at a table of contents, your human brain intuitively recognizes the hierarchy. You scan a line and you instantly spot, okay, there's the chapter number, there's the title, and way over on the right, there's the page number.
Right, my brain just kind of automatically categorizes the pieces.
Exactly, but to a PDF generation program, unless it is specifically instructed otherwise, a string of Chinese characters is just a dumb, undifferentiated block of data.
It doesn't know it's reading a book?
No, not at all. It doesn't inherently know which part of that string is the number. It just sees graphical shapes occupying horizontal space on a page.
And because Chinese numerals use different character counts for different values, right? Like the word 3 might be one character, but 300 takes up more horizontal space.
Precisely. The physical width of that chapter heading shifts constantly from line to line depending on the number.
Oh, I see. And that shifting width is what pushes the trailing text, like those little dotted lines, the leaders, or the page numbers. It pushes them entirely out of alignment.
Yes. So to get that uniform gallery wall you were talking about, Aang can't just treat the chapter title as a single opaque block anymore. They have to dissect it. They have to isolate the specific variable causing the problem, the number, and standardize it.
Wow, okay. So we've identified the problem. The changing width of these Chinese characters is ruining the page margin. But identifying the problem is the easy part, right? How does a rigid computer actually separate the math from the language?
Well, to isolate that variable, Aang decides to break the text down into its base linguistic components. And the log actually provides a really specific example chapter header to show how this works.
Right, I have it right here. The example header is this kit.
Perfect. So in order for the computer to safely convert the number inside that specific string of text, Aang identifies 5 distinct components.
5 for one short title.
Yes, 5. First, there's a prefix. In this case, it's the Chinese character D. This functions as an ordinal indicator. It's kind of similar to the the in fifth in English, or maybe the no before number 5.
Okay, so it's a marker that says, hey, a number is coming.
Exactly. Then comes the second part, which is the actual number itself. In this example, it's Akiam Sendai, which translates to 300. That's the target. That's the piece Aang actually wants to change.
Right, that's the troublemaker ruining our margins. So what's the third part?
Following the number is the unit. Here it's the character Zhang, which simply means chapter.
Okay, prefix, number, unit. Got it.
And the fourth part is full width colon, which is just acting as a visual separator.
Right.
And finally, the fifth part is the descriptive suffix. In this case, Uyuxian, which is the actual unique title of that specific chapter.
So by breaking the string apart this way, the developer is essentially isolating the target variable, the number, from all the static text surrounding it.
Yes, it's all about establishing strict predictability out of complete chaos. You box in the unruly part so you can control it without accidentally damaging the rest of the sentence structure.
You know, it feels a lot like grammatical sentence diagramming from grade school.
Oh, that's a great comparison.
Yeah, like when you had to draw those little lines to separate the subject from the verb and you're isolating the prepositional phrase just to understand the underlying architecture of the sentence.
Exactly. Aang is doing exactly that, but they are creating syntax rules for a machine instead of a middle schooler.
Right. But let me challenge this approach for a second because it sounds like a lot of work. Is it really necessary to slice a simple title into 5 distinct pieces just to change a single number?
It does seem like a lot, right?
Yeah. Like, why not just write a quick script that tells the computer, hey, scan the line, find the number, and swap it out with digits? Why the 5-part dissection?
It seems like overkill to us because human brains process context automatically, like we said earlier. But a computer doesn't actually know what a quote-unquote number is in a string of text unless you explicitly define its boundaries.
Okay, but if it's a Chinese numeral character, couldn't you just tell it to look for those specific numeral characters?
You could, but think about the danger there. If Aang simply instructed the program to find any number character and replace it, what happens if the chapter title itself contains a number?
Oh. Oh, wow. I see what you mean.
Right. Let's say the chapter is literally called The 3 Secret Doors.
The program might convert the word 3 in the actual title text instead of the chapter number at the beginning. It would completely mangle the author's work. It would print as Chapter 300, The 3 Secret Doors.
Exactly. The computer is completely obedient, but it lacks all common sense. By explicitly defining the prefix, the unit, and the separator, Aang builds a highly specific map for the software to follow.
Ah, so the program is told, look, find the prefix, then find the unit, and understand that whatever sits exactly between those 2 specific markers is the chapter number.
Yes. Change that specific piece and ignore the rest of the string entirely. It's incredibly safe.
You have to put guardrails around the data so the program doesn't just go rogue and alter things it shouldn't.
Okay, that makes perfect sense. So now that we've mapped out those 5 linguistic pieces, we need a digital container to actually hold them, right?
All right, we need a place to store our diagram's sentence in the code.
And this naturally leads us right into Aang's actual Haskell code. In the log, Aang introduces a brand new Haskell data type to handle this, and they call it header info. Right, and this new data type is specifically designed to store those 5 isolated segments we just talked about. The fields in the code map directly to our diagram.
Let me look at the log here. Yeah, it has his prefix, high number, high unit, his separator, and his suffix. It's a one-to-one match.
It is.
But here's where it gets really interesting for me. Looking at the actual Haskell code for this data structure, Ang repeats a very specific word for almost every single field.
The maybe type.
Yes, it's written as a maybe char for the prefix, a maybe text for the number, a maybe char for the unit, and a maybe text for the separator. The only field that drops the word maybe is the suffix, which is just listed as text.
If we connect this to the bigger picture, the use of that word maybe speaks directly to the tension between strict functional programming languages like Haskell and the chaotic nature of human linguistics.
Because Haskell is notoriously strict.
Yep, incredibly strict. Haskell requires you to be absolutely explicit about your data types.
Yeah?
You cannot just throw unexpected data at a Haskell program and hope it compiles. It will crash. So the maybe type is Haskell's way of encapsulating an optional value. It's a built-in acknowledgement of uncertainty. A value of type maybe either contains something or it contains nothing at all.
It reminds me of, you know those highly specialized Japanese bento boxes?
Oh, yeah, with the little compartments.
Exactly. You have these distinct, perfectly carved out compartments. There's one for rice, one for your protein, maybe a tiny little square compartment for a pickled plum. Every single piece of the meal has its exact dedicated spot.
That is an excellent way to visualize how Haskell allocates memory for these data structures.
Right, but depending on what you pack for lunch on a given day, some of those compartments might be empty, like you might skip the pickle today.
Sure.
But the compartment itself doesn't disappear. The box remains perfectly organized regardless of whether a specific section actually has content inside it that day.
Yes, and that structure implies necessary flexibility. Because, as we established, human writing is wildly inconsistent.
It really is.
Not every single chapter title in a book will perfectly feature a prefix, a number, a unit, and a separator. Some chapters in a novel are just a standalone title, like an epilogue.
Oh, true, or an introduction.
Exactly. Some might have a number, but no prefix. By leveraging that maybe type, this header info data structure accommodates all those human inconsistencies without breaking Haskell's incredibly strict rules.
It's brilliant.
It tells the compiler, hey, check this compartment. If there's a prefix in there, store it. If it's empty, handle that gracefully and move on without throwing a massive error.
And the suffix, the actual chapter title part, that field doesn't get a maybe because every chapter header fundamentally requires some actual text to exist as a header in the first place.
Right. The suffix is the mandatory meat of the bento box. If you don't have that, you don't have a lunch.
You just have an empty box.
Exactly. You always have to have the core content. The metadata surrounding it, the numbers, the units, the prefixes, those are the optional maybes. It's a really elegant method of building a rigid digital structure that can bend just enough to survive contact with the reality of how human beings actually type.
Okay, so having this perfectly organized header info bento box is great. It's beautiful, but it has to actually integrate into the larger refrigerator, right? The overall architecture of the ebook document itself.
Right. It can't just exist in a vacuum. It has to be used.
So the log shows Ang modifying the fundamental block data type. And this is the code that represents the actual content blocks forming the entire document body.
Yes. The previous iteration of a header block in their code was pretty simple. It was defined by 3 core components: a header type, an int, and text.
Let's clarify those components for the listener really quickly. The header type basically dictates the kind of header we're dealing with. The integer dictates the hierarchy, meaning it tells the document whether this is an H1 main title, an H2 subheader, or like an H3 section header.
Right, the sizing and importance.
Exactly. And then the text part simply holds the actual string of words.
And in this log, Ang expands that foundational definition. The new block header is updated to include the header type, the int, the text, and now it also includes our brand new header info structure.
Wow. So they are taking this granular, perfectly deconstructed linguistic map we just spent all this time talking about and injecting it directly into the core foundation of the document.
They are. And this raises an important question about invisible dependencies in software engineering.
How so?
Well, before this update, the header block just held raw, dumb text. It was opaque. Now, it carries a deeply analyzed, parsed version of that text everywhere it goes in the system. Ang actually concludes the log by stating that this new structure provides the necessary groundwork to clean up the table of contents formatting.
Right. They say it sets the stage, and then the post just ends.
Yep, that's the end of part 174.
Aang literally says, in the next post, I will walk through the actual implementation for converting the Chinese numerals into their numeric digit equivalents.
A bit of a cliffhanger.
So what does this all mean? I mean, I have to act a little exasperated here on behalf of everyone listening. Wait a minute. We just went through all this intense dissection. We diagrammed a sentence into 5 parts. We defined new types. We built a custom Haskell bento box with all these maybe compartments. We upgraded the foundational architecture of the document block, and we haven't even converted the number yet.
Not a single number has been changed, no.
Why did we just spend an entire developer log just on the setup? It feels like we did all this work for nothing to happen visually.
I get the frustration. I really do. But it perfectly highlights the deeply methodical nature of software engineering. You simply cannot execute the flashy part, the actual script that swaps the characters and fixes the visual glitch on the page until the underlying invisible scaffolding, the data structure, is perfectly in place.
It's the equivalent of spending weeks pouring and perfectly leveling a concrete foundation for a house.
It's exactly what it is.
And if someone walks by and asks why you haven't painted the living room walls yet, they're entirely missing the point of the labor. If you start painting without a foundation, the house falls down.
It collapses.
Yeah.
If Aang tried to blindly execute a script, replacing characters without that header info framework to protect the data, the PDF generator would crash the moment it hit an unexpectedly formatted chapter. Or worse, as we discussed, it would overwrite the wrong text and ruin the book.
Right, the 3 secret doors problem.
Exactly. The log proves just how much invisible prep work goes into even the simplest, most mundane digital operations. The actual code to convert the numbers, that will probably be 3 or 4 simple lines in the next post.
Really? Just a few lines?
Probably. Building the secure environment where those 3 lines can execute safely without destroying the document, that is the real work.
The prep work really is the actual work. Wow.
It always is in programming.
Okay, so recapping this incredible journey for everyone listening. We started with a really annoying, relatable visual glitch, right? An uneven table of contents in a generated PDF, which was caused by the unpredictable horizontal width of Chinese numerals.
And solving that glitch required Aang to deconstruct a standard Chinese chapter title into 5 distinct, logically isolated linguistic pieces just to establish a baseline of predictability.
From there, we watched Aang build a custom Haskell bento box, that header info data type, using that highly flexible maybe syntax to organize those linguistic pieces perfectly for an incredibly strict compiler.
And finally, that brand new structure was fully integrated into the core architecture of the document block itself, laying all the invisible groundwork required before a single number could actually be transformed.
It is honestly a staggering amount of invisible labor just to make a simple list look perfectly clean and aligned on a page.
It makes you appreciate your PDFs a little more, doesn't it?
It really does. And actually, I want to leave everyone listening with a new lens through which to view your daily tech usage.
I love that.
Later today, think about the most beautifully formatted, seamless digital document or website you've scrolled through recently. Notice how perfectly the margins align, how flawlessly the text is spaced on your screen.
It doesn't happen by accident.
No, it doesn't. Consider the invisible, painstaking dissection of human language that had to happen behind the scenes by developers like Aang, just so that simple list looks perfectly right to your eye. Every smooth, effortless page of text you read hides an incredibly complex, whirring machine of hidden data structures.